All right, for this problem, we have a motor that it says it's capable of producing 165 watts. It says that and then it wants to know the maximum speed that the motor can turn while lifting W2 is closest to. And the reason that phrasing is important right there is that you might be able to look at this and tell that if W2 is being lifted, what's W1 doing? Right? W1 is dropping if W2 is going up based on the direction that the ropes are being wrapped around their respective spools. Okay? You see that? Okay, what do we know here? We know the two weights. We know the diameters of the drums. Okay, we know a few other pieces of information as well that may or may not be relevant because the motor is just supplying torque to this shaft. What we need to know is how much torque does the motor need to apply to the shaft to basically cause it to move at a constant speed? Right? How do I do that?
Solve our power equation.
Okay. We're not quite there yet. So what we need to do is probably solve the torque part of this problem first. Right? His suggestion was we could maybe solve the power equation. We will get there. But what we need to do first is look and see just how much torque does the motor need to apply to make this thing move at a constant speed. We can do that based just on the weights and the radius values of the pulleys, right? And what it's going to be, that torque that it has to apply, is going to have to be equal to W2, 230 newtons, times the radius of this pulley, which is DC over 2, right? Because the force times the radius gives you the torque that just that weight is being applied to that pulley, right? So from just weight 2, the amount of torque being applied is just that weight times the radius of this pulley. So that's just going to be 20 centimeters over 2. Okay? And then, this is probably where most people get tripped up. The direction of torque applied by W1 is also just that weight, which is 110 newtons, times the radius of that pulley, dB, right, is 10 centimeters. And that would be divided by 2 to get the radius. But where most people are going to mess up is they're going to probably want to add these two together. And that's not right. Why not? They're going opposite directions. The direction of torque that W2 is applying here goes this way, whereas the direction of torque that W1 applies goes that way. And the net torque that we have to react over here is going to have to, basically be the difference between those two because they are opposite directions. Right? So I'll basically subtract here, and this will give me a torque value. Okay, so 230 times 20 over 2 minus 110 times 10 over 2. Okay, this will be 1750. This is going to be in Newton centimeters. Is that the most convenient units, you think, to deal with when we're thinking about power? Perhaps not. What should I maybe multiply this by? Okay. Yeah, so 100 centimeters in a meter. Right? So I'll basically I'll divide by 100 more or less. Right? So let me go ahead and take this and divide by 100. Right? So that gives me a number of Newton meters, 17.5 Newton meters. How's that useful? Okay. P is equal to T omega. Okay. For our problem, we know that P is 165 watts when it's moving as fast, or it's producing as much power as you can with that motor. Right? This is going to be equal to that torque, 17.5 Newton meters, times omega. Okay. What's a watt? Okay. So let me do this. Omega now is equal to 165 watts, and you're telling me here that a watt is a joule per second, and what's a joule? Okay. So in 1 watt, there is 1 Newton meter per second. And this is going to get divided by 17.5 Newton meters. And what you'll see there is that we can get rid of the Newton meters. We can get rid of the watts. And what are we left with here? 165, all right, divided by 17.5. Okay, 9.429. What are the units? 1 over seconds, right? What does that imply? Yeah, the angular units, when you use this P equal T omega, the angular units have to be in radians, right? So this is a number of radians per second. So what do I need to do to be able to know how to answer in my choices there? Okay. Yeah, so basically what was just suggested here is that we know that we have 60 seconds per minute. Okay. And there are 2 pi radians in 1 revolution. Okay. And if I multiply by those factors there, it'll give me a number of RPM. Okay, so this value times 60 divided by 2 pi. Which gives you 90.04 RPM. Which fortunately that's one of the answers. Okay? Any questions on that one?